Now, let's handle the equal case first, because this one is relatively easier. All right, so for the equal case, we can find the rank K element immediately. Okay, all right. So let's do some deep analysis. Because this K number could be even or odd. So we discuss two cases, odd case and even case. For odd case, these two numbers can be represented in this formula, K plus 1 over 2. Even case, K over 2. Okay, all right. Now, so let's look at how do we find the rank K element. All right, so here, S sub K, that's the notation for the rank K element. Okay, so we use a simple notation, rank K element, S sub K. All right. So for the other case, here, the solution is this, A of M1A. Why? So let me explain. Okay? We can see that. Even case, S sub K equals B of M1B. Yeah. So how do we see it? For odd case. So let's look at these two arrays, these two parts. All right. We know they are equal. Okay. Then let's draw this line. Okay. Examine these elements. How many elements do we have? Look at that. How many elements do we have? Okay. All right. K minus 1. Okay. Double. Yeah. Because each one, K minus 1 over 2. So double K minus 1. Okay. So you can see at the left-hand side of this vertical line, there are K minus 1 elements that are smaller or equal to the elements at the right-hand side of this line. Okay, yeah. Now, the first element, the smallest element at the right-hand side of this line will be the kth smallest. So that's why this is the kth smallest. Okay, so that's for the first subcase. Second subcase. All right. So let's consider the second subcase, the K even. So this time, let's consider these two arrays. Also draw a vertical line like that. Okay, and we know there are K minus 2 this time elements at the left-hand side of this bar. Left-hand side, K minus 2 this time. All right. Then the right-hand side, okay, right-hand side, we need to find the second smallest. Although they are equal, but we treat the first smallest, second smallest. So that's why we take this B as the, yeah, so A, this one as the K minus 1 smallest, and this B as the kth smallest. Okay, so assume we use their natural order. Okay, so A, so if equal, we take A first. Yeah, assume in that way. Yeah, so you can see we can find the kth smallest in that way. All right, yeah. Now, unequal case. Yeah, okay. Unequal case. This time we need to use elimination. Yeah. How many elements can we eliminate? Yeah. All right. So let's consider the odd case. Yeah. Because for even case, very similar. Yeah. One of the two cases should be enough. All right. So for this case, we need to do eliminations many times. So many iterations. So let's look at the first iteration. We compare these two subarrays. Which part we can eliminate them immediately? So let's look at this question. Which part we can eliminate them immediately? All right. So we assume this situation. Yeah. Okay. Now let us look at this element. Can we see this element beats at the most k-1 element? At the most. This is important. At the most k-1 elements. Because this one first can beat these elements for sure, right? We already know, because based on the order, this element can beat those elements for sure. But can this element beat these elements? Not sure. But it's possible. It is possible to beat these, but not for sure. Okay? All right. But other than this part, the remaining, it has no chance to beat. Okay? For the remaining elements, this one has no chance to beat any. So that's why we say at the most k-1. These are k-1 elements. That element can beat, has a chance to beat at the most k-1 elements. Okay? Yeah, based on that observation, based on this observation, beats at least k-1 elements, what conclusion can we make? Yeah. Because the best you can do, beat k-1 elements. That means this element less than or equal to k sk, the rank k element. It cannot be greater than rank k element, right? Because if it is greater than rank k element, it can beat at least k elements, right? So that's not true. So less than or equal to rank k element. All right. Then this one less than or equal to k. Then these elements are strictly less than sk. How about that? Strictly less than sk, then they can be eliminated immediately, right? This circle, all the elements in this circle can be eliminated immediately because they are strictly less than sk. Okay? Yeah. So that's the argument. All right? All right, so we cross out that part. Yeah. But when we cross out that part, we keep this element. That's why the line draw here. Okay? We still keep the element at M1A. All right. So we eliminate this portion. That's pretty good. Next, from the larger side, can we eliminate some elements at the larger side? Yes, we can with a similar analysis. So this time, let's consider the elements, this part. What are those elements that can be eliminated for sure? Yeah, let's consider that. Okay, all right. Let's look at this B element, BM1B. How many elements can this one beat? All these, right? All these elements, this BM1B can beat. Okay. How many elements this B can beat? At least a K, right? That means this element is already greater than sk, because it can already be at least k element, right? So that means all the elements greater or equal to this B part can be eliminated. Okay, that means this part can be eliminated because all the elements are greater than the sk. Okay, all right. So after these two parts elimination, how many elements are left? 1/2 of the original size. Exactly 1/2 of the original size, right? So you can see one comparison. The conclusion is one comparison can reduce the problem size by half. Every time when we do one comparison, we reduce problem size by half. Another comparison reduce the problem size another half. We keep doing this until we get the problem size 1. The last step, problem size 1. How many comparisons do we need? Okay, log base 2 of k. That's the solution. So that's the log base 2 function we use. Because every time we cut the data size by half, cut data size by half, and finally, the number of times we do the comparisons, log base 2 function. Yeah. All right. So that's pretty close to our final answer, but there are several remaining cases we need to consider. Then we complete the whole discussion. Yeah. So the base case we already covered. The most basic case we covered. Yeah. Then the remaining cases, we still have some related cases. We need to look at it. Yeah. So let us assume m less than n. Okay, less than or equal to, yeah, equals okay. Okay, yeah. Just one is no greater than the other. So for easier discussion, yeah. All right. Now you can see we can draw the diagram in this way. This is the union of the two arrays. Union of the two arrays. So this part corresponds to n, then corresponds to n, right? But after we merge the total array m plus n, right? Yeah. So we imagine after these two arrays are merged, yeah, we get m plus n elements. All right. But we do not do the merge. Yeah, we just, imagine in that way. All right. When k in this part, we solve it. Okay. All right. Next, we want to consider the k in this part because it's possible. Consider k in this part. Okay. The thing we want to explore, these two parts are symmetric. Symmetric. From the diagram, you can see symmetric. So if we flip, right, we put a mirror in the middle, we flip, the same. Okay. Yeah. So symmetric. So we want to take advantage of the symmetry here. So how do we take advantage of symmetry? All right. So the observation like this. When k in this range, that is this part. Okay. All right. Can we convert the kth smallest element to this n plus n plus 1 minus kth largest? Because they are the same thing, right? For example, the n plus n smallest, that's the first largest, right? So that's why m plus n plus 1 minus k, okay? Yeah, largest. Yeah. So you can look at from the smaller side, but you can also look at from the larger side. If the k number is too large, you'd better look at from the larger side, because then that number will be smaller, okay? Because this 1 is a small number, okay? All right, so based on this observation, we can do it in this way, yeah, this conversion, yeah. All right, so we do some adaptation like this. Counting from the left is equivalent to counting from the right if we change the rank number to a different rank number, okay? Yeah, and we know when k is in this part, that number less than or equal to n, okay? Yeah, so here we use u equals that number, the conversion, okay? Yeah, so then the u will be less than or equal to m, okay? So then the rank number k, we count from the smaller side, corresponds to the reverse rank number, because we come from the larger side, the u, okay? So with that observation, now can we do the same thing as we did before, the binary search, right? So the 2 array, A array, B array, okay? B array, yeah, B array, how about I draw in this way, okay? This time, can we look at the k elements from the larger side and look at the k elements from the larger side and do the, elimination the same way as before, right? Yeah. So we use that, similar method. We can find a solution for this part, okay? All right. So we can solve k in this part. Yeah. The last case, the k in the middle. When k in the middle, so now let us do some more, using different way to solve it. Yeah. Because this time the k is in this range. Okay. Now, so let's draw the diagram in this way. The k, yeah, we can, from A array, we can cut 8 elements. The remaining can be eliminated, right? Yeah, safely eliminated. But for the B array, if we try to cut the k portion, we know longer than the B array. Longer than the B array. So we won't have anything here, okay? Yeah. All right. So here, can we do some thinking like this? Can we put some imaginary elements here? Imaginary elements here without causing any problem. So we want to add some, fake elements there without causing any problem. Can we do that? Try to think in that way. Okay. There is one way we can do it. One special way we can do it. Okay? Yeah. Without do any damage in our analysis. Okay? We try to use infinity elements there. Can we pack the remaining part, infinity elements there? You may argue, how do we get infinity elements, right? All right, so here, we just imagine some special symbols. We use some special symbols as infinity. Okay. But in our program, we won't really use infinity. Okay. In our program, we will conceptually use infinity, but in our operations, we will get around infinity. But in our analysis, in our thinking, we can use infinity in our thinking. Okay? All right, so in that way, thinking using infinity, but in our implementation, I think we can easily get around it, because infinity can be any other elements. infinity can be any other finite element. So we just use this property. So we can do things well for the infinity part, right? Yeah. So then when we do that way, so you can see based on our first part analysis, we get bigger of log k. So that is in this category, bigger of log n. Yeah, less than, at least, less than that, right? And in the first general case discussion, we have that m minimum of m and n. So if we combine these two cases, definitely we have our bigger of log k in this category. Okay, so no problem in that category. So that's, you can see if we can, so here, this is the idea, the analysis, the thinking. So if we get all these things working smoothly, then we solve the problem. Okay, all right. So this example, pretty complicated. Yeah. So try your best to understand. Yeah. Pretty complicated. Yeah. The reason here we use the general m and n number integers. Yeah. But I may give you some concrete numbers. For example, m equals 5, n equals 7. So things like that. If you have concrete number, can you eliminate certain elements explicitly, right? So think about it in that way. Yeah. Then you can understand this method much better. All right, so let me stop here. So we complete this whole lecture. Lecture 11, part A, part B, all completed. Yeah. All right.